Hi everyone. So in this video, we're going to go ahead and talk about something called the combined gas law, which is going to take those four gas laws we've talked about already. So Boyle's law, Charles's law, Gay-Lussac's law, and Avogadro's law, and put them all together. So although the previous four equations are pretty simple, it's a lot to memorize and keep straight. So we can combine all of those into just one equation they have to memorize, which is the combined gas law, making things a little bit easier. The other benefit of the combined gas law is it allows us to alter more than one variable at a time. So we could change the pressure and the volume, or the temperature and the volume, or whatever it is that you want to change. And that's much more realistic for everyday life. Okay, so I'm going to go ahead and go through a derivation of the combined gas law. Now, if you're in CP chemistry, do not panic about this at all. The only thing I really want you to take away from this is the final equation, and also the fact that this all comes from someplace. For my honors chemistry students, what I want you to take away from this is all those different laws, they come together and kind of get a sense of we're not just making things up. There is a fundamental basis for all these different ideas. But again, just really focus on that final equation. I will never ask for any of my students for you to be able to derive the combined gas law on your own. So the first thing we need to do is we need to start off with all the different relationships between the different variables that we've discussed so far. Remember, for Boyle's law, it's inversely proportional to the pressure. That's what that little funny curly Q in the middle means. Proportional, and since it's the fraction 1 over P, that's where we get the inversely proportional. Charles's law is directly proportional for volume and temperature, and Avogadro's law is directly proportional for volume and number of moles. Now, one thing I want to point out, we do not need to include Gay-Lussac's law because it will just magically appear once we put everything else together. So we take those three different ideas, those three different relationships, and we can squash them all together, okay? So volume is proportional to the number of moles times the temperature over the pressure, okay? So that gives us that relationship. Well, and instead of just saying proportional to, we want to get a specific value. We don't want to be so wishy-washy. So we can say that the volume is equal to some constant times the number of moles times the temperature over the pressure. Okay, so that lets us get to a more concrete equality. So once I have that, I'm going to multiply both sides by pressure over the number of moles times temperature. And that basically allows us just to get the constant by itself. So we're just rearranging our equation. And once we have that, we can just kind of rewrite it and simplify it to get PV over NT is equal to some constant. Okay, and then finally, because constants are, well, constants, we know that the first constant must equal the second constant. So that gives us the final combined gas law. Okay, so if I've lost you so far, do not worry. It's okay if you completely gloss over everything that I've talked about so far. But that green box, everything inside, that's what I want you to take away from this. So P1 times V1 over N1 times T1 equals P2 times V2 over N2 times T2. So just like before, the ones are the initial values, the twos are the final values. P is pressure, V is volume, N is the number of moles, and T is the temperature in Kelvin. Okay, for the other variables, you can have different units as long as they are the same on each side. So pressure, remember, could be in atmospheres, bars, millimeters, mercury, doesn't matter as long as it's the same on both sides, but temperature must be in Kelvin. Okay, so let's go ahead and try out an example of this. Okay, so let's try an example of this. So remember, this is our combined gas law equation. And one thing I want to point out that if you have a variable that doesn't change from the beginning to the end, you can go ahead and cancel that out from both sides of the equation. You can kind of simplify things from there. So as we read through our example, it tells us if I have 17 liters of a gas at 67 degrees Celsius and a pressure of 88.89 atmospheres, what will the pressure of the gas be if I raise the temperature to 94 degrees Celsius and decrease the volume to 12 liters? Okay, so as I read this, I'm thinking about a few things. So my temperature I see is in degrees Celsius. I'm going to need to remember to change that to Kelvin. And I also want to think about the paired values, the ones that are grouped together. So I begin with 17 liters of a gas at 67 degrees Celsius and a pressure of 88.89 atmospheres. Those are all grouped together. So those are going to be my ones. And then my ending, I have my new temperature. I don't know my volume. Or sorry, I do know my volume, but I don't know my pressure. So I'm going to go ahead and start to kind of write down and label those values. Okay. And the other thing that I see is I do not have moles listed anywhere at all. I'm taking that same gas. So because of that, I'm going to simplify my equation a little bit and just write it. P1 times V1 over T1 is equal to P2 times V2 over T2. Again, my number of moles, because it's not being discussed, I can assume that is staying constant. So I'm canceling off both sides of my equation, my ones and my two side, to simplify to this equation. Okay, so let's go ahead and start writing down our values. So my initial pressure is really, really high, 88.89 atmosphere. So to give you a point of reference, atmospheric pressure at sea level on a typical day is 1. So this is really high pressure. Volume is 17 liters. And my temperature is 67 degrees Celsius. But don't forget, we need to change that to Kelvin. So we're going to add 273 to that value. So when we do that, 67 plus 273 gives me 340 Kelvin. Okay, so then for my twos, my pressure at my higher temperature, that is my unknown. So I do not know that value. My V2, that is 12 liters. And then my T2, that is 94 degrees Celsius. And again, I add 273 to that value to get my temperature in Kelvin. So 94 plus 273, that is equal to 367. Okay, so now I'm going to go ahead and plug those values into my equation. So my initial pressure is 88.89 atmospheres. My initial volume is 17 liters, and that is over an initial temperature of 340 Kelvin. For my final side, my P2, I do not know. My final volume is 12 liters, and my final temperature is 367 Kelvin. Okay, so basically what we're going to do now is get P2 by itself. So I could cross multiply and then divide, or the easier thing to do, I'm going to multiply both sides by the inverse of this fraction. So I'm going to take 367 divided by 12 and multiply that by both sides. So I get 88.89 atmospheres times 17 liters over 340 Kelvin, and that's being multiplied by 367 Kelvin divided by 12 liters. And you know that you're doing this right if your units cancel out. So my liters cancel out, my Kelvin cancel out, and I'm left with just atmospheres, which is good because that's what I want for my unit for my pressure. So once we have this, we're going to multiply the numbers on the top, divide by the bottom. So 88.89 times 17 times 367, and then divide that by 340 and divide by 12. Okay. So P2 is equal to 135.93, but as always, we want to think about sig figs. So as I look at my given values, I see that the least number of sig figs is 2. So I need around 135.9 to 2 sig figs. So I'm going to chop it off between the 3 and the 5. So 135 is going to get rounded up to 140 atmospheres of pressure. Okay, so let's go ahead and we have the U-try. So I have an unknown volume of gas at a pressure of 0.50 atmospheres and a temperature of 325 Kelvin. If I raise the pressure to 1.2 atmospheres and decrease the temperature to 320 Kelvin, the final volume is 48 liters. What is the initial volume? So that's going to be my V1. So go ahead, try this problem on your own. Again, it doesn't talk about moles, so we can simplify that equation just like we did up here. So try this on your own, and then come back and we'll go through the answer together. Okay, so if I read through this, my paired values that I start with are 0.50 atmospheres and 325 Kelvin. And then my final values are my 1.2 atmospheres, my temperature of 300 Kelvin, and my final volume of 48 liters. So P1 is equal to 0.50 atmospheres, so much lower than our last problem. V1 is unknown. That's what I'm being asked to find. And then T1, they are nice and give us the temperature in Kelvin, so I don't need to convert in this case. So 325 Kelvin. Now for my final parameters. P2 is equal to 1.2 atmospheres. V1 is equal to 48 liters. V2 is equal to 48 liters. And then my temperature, T2, is again in Kelvin, so 320 Kelvin. So let's go ahead and plug in our values. So P1 is 0.50 atmospheres times V1 divided by 325 Kelvin. And that is equal to 1.2 atmospheres times 48 liters divided by 320 Kelvin. So again, I could cross multiply and divide, or I can just multiply by the inverse of this fraction. So V1 is equal to 1.2 atmospheres times 48 liters divided by 320 Kelvin times the inverse of this fraction, so 325 Kelvin divided by 0.50 atm. So again, I want to check that my units are canceling out. So atmospheres cancel and Kelvin cancels, which leaves me with liters, which is a good unit for volume. So if I go ahead and put this into my calculator, 1.2 times 48 times 325, and then divide that by 320, and then divide that by 0.5. So that gives me an answer of 117 liters. But again, I want to think about my sig figs. So if I look here, the smallest number of sig figs I have is 2. So this 117 is going to get rounded to 120 liters. So I hope that helps. If you have any questions with the combined gas law, please go ahead and let me know. Otherwise, have a great day, everyone. Bye.